or maybe some Cartesian power or product of them. Okay, for every such intersection, I'm going to put just a relation symbol in the language for this structure. And the theory is going to say that it behaves exactly as Q and C behave inside DCF. Okay? So what I'm doing is I'm just throwing away the irrelevant bits inside DCF. So I'm looking just at the structure, at the restriction of the structure to this Q and C.
So there's no field structure.
So there is a field structure on C. So in particular, C is a subfield, is a definable subfield, so all the field structure on C is present. But there's no field structure here. However, there are some remnants of the field structure. So for example, if I have, so let's look at an example. For example, so suppose that Q is x prime equal to x over 2t, then in DCF, I have a definable function, so f from Q to C, which says that f of x is x squared over t. Okay, so this is some function. So of course, if I take any, for example, order 1 differential equation, I can look at this function. But in general, this function is not going to go into C. If I have a different equation, then probably the values of the functions are not going to be in C. And so when I restrict it to the structure that consists of just Q and C, I don't get anything interesting. But in this case, I am going to get an interesting function. Okay? So I have this function. It's an interesting function from Q to C. And so I will have this function also in this structure.
Rational function.
Yeah,
So f is a definable function in Q.
Moshe, why is f of x a constant? I'm confused.
Because if I
Squared over t.
Yeah.
Because x is secretly the square root of t.
X is the square root
Oh,
of t.
I see. So, okay. So you're looking at the solutions.
So this follows
Okay.
formally just from the fact that
Okay.
I have this equation.
You're not looking at determinants. So what's the ground field here is just
KT.
KT.
So the ground field is
C of t.
ground field is for example what could be any for example C of t.
Yeah.
I mean anything that contains
Or
t to write down the
R.
equation.
Better
Or R of t.
R of t.
Could be R of t, yes.
For your philosophy.
Yeah, I mean here it could be just Q of t.
Yeah. Q of t.
I mean I just need enough
I see. Oh.
enough things in the field to write down the
So you're
equation.
taking a solution in f of x equals x squared over t. Yeah, I see.
Okay?
Why is this
I don't, I
function
think.
not constant value 0?
Sorry?
It seems that this function has a constant value 0. So it's
Yeah,
not
no.
a terribly interesting function.
No, the derivative of it has constant value 0, which means that it's in the constant.
Yeah.
Which means it's a constant. Yeah, that's where I.
Yeah, so this is an interesting function into C, which means it's a
Yeah, I
not very
see,
interesting
yeah.
function into the.
Yes.
Okay, so it's some structure so that I mean, so it's always an n-dimensional vector space, but the additional structure depends a lot on what is the actual equation.
Yeah.
And the point is that it really contains everything you need to know.
I see.
Basically, because so first of all, because of quantifier elimination, when I say that I restrict all formulas, it's enough to look at quantifier-free formulas. But on the other hand, because of again some properties of of DCF, it's I mean it's actually the same to think about the equation inside DCF or just inside this structure, but just we throw away all the stuff that is in there. Okay, now by the way here, so as I said, so T will say that C is actually algebraically closed field and containing CK. Okay, so I will have constants for elements of CK here. Okay. Question?
Is C equal to E? That was the question.
No, there's no E anymore. E only appeared in the
Oh,
in the
okay.
definition. Okay, it will appear again.
So now I'm not sure
In
where
the
C
example
is.
where you have the I cosine 2t or something like that, where I comes as a formula,
So at this point,
expressible in terms of the solutions. So how does it work in this model here?
What is C?
so
So Q would be the vector space driven by the I sine t or sine 2t or sine 2t.
The constants
So
are different.
at this point, we're not thinking about particular fields at this point.
Yeah. So
Oh,
also
that makes a huge difference.
But what will happen is you will have, so over that field, it means that you will have some algebraic. It will be similar to this, just a bit more complicated. It will have some algebraic equations, but the point will be that whenever you take
those will be
whenever-
included in your new structure then, right?
yeah, it's covered by this. The point for that structure is going to be that when you take a structure in which okay.
I sine squared plus I cosine squared is minus
Okay, let me give one small definition.
No, the other one is that having the I in there.
So by a T-field structure,
I cosine t.
No. I as a single thing that is expressible in terms of this.
Well, no, but you do that.
An example.
What? Oh, I see, yeah.
is there a question?
You have a question?
So a T-field structure is a subset of a model of T-field which is closed
C
under definable Okay, so if you have a structure, it means that you have some field, not necessarily algebraically closed, and then some set of solutions. Okay, by the way, notice that there's no differential structure here, but you can think of it as a set of solutions of the equation.
It shows though that culture is on the right track.
Yeah.
So, that's a structure. And what I was going to say is that in this example, in this first example that I gave, if you have a structure, if you have a T-field structure where the Q part has full dimension, so has dimension 2 in that case, then so you will have a definable function like this, but maybe more complicated, and I is going, and that definable function I is going to be in the image, okay, and that's how you see that example in this case. And this definable function will be part of the structure.
So, but then the theory T tutor will be very different for the two different examples.
Yeah.
Yes, exactly. So,
Yes.
so that's what I said. T tilde it depends very much on Q.
Right.
So, yeah. So it could
even
it could easily be that it could easily be.
even if I have two Qs that are isomorphic as vector space over C, the T tutor could still be different.
Yes, of course. Yeah. So
Yeah.
to be isomorphic as vector space just means that they have the same dimension.
Right.
So yeah. So but then you have extra structure. So for example, it could also be that this is the only structure is the vector space structure, and this exactly means that the Galois group is the full.
No, but
GMV.
what I'm saying is that you actually need to look inside Q of the
Yeah.
solutions
yes.
itself.
That's what you get from this extra structure. So you sometimes have extra structure.
Moshe, if instead of n linearly independent solutions of an order n equation, you go back to your definition of x prime equals ax,
Yeah.
and you take, instead of Q, you take a matrix in the general linear group, or whatever. Not instead
That's
of
what
Q.
I'm taking. That's what
Yeah.
You're taking,
Yeah.
oh, what vector
Inside.
space are you taking then?
Over
So
Q.
I'm looking at this. So this is an n tuple of variables.
Oh, it's an n tuple, not a matrix equation.
Yeah.
I will also be looking at the metrics. It doesn't matter, but
Then
so
Oh, you just said it was matrix.
okay. One moment. So A is a matrix over K,
It can
right?
be either.
So I have constants in the language for K. So this is
Yeah,
a,
that's all right.
This is a legal
That's already
formula.
there,
Sure.
yeah.
And also the matrix equation is also in,
Yeah,
in
So
the same
why
way.
do you need Q added to the theory, or?
So Q is the set of solutions.
Solutions, right.
But I could also work with
That
the
could
set
be a
of-
matrix.
So I could work with either because
Oh, okay.
if I start with with Q, I also have Cartesian powers here.
Yeah.
And so I have Q to the end.
Ah,
and,
yes.
and inside it I have the subset of linearly independent vectors, n tuples of vectors, which is a definable subset. And on that thing I have.
Yeah, that I see.
have
But
the-
what I'm wondering is, I'm used to working with matrix solutions.
Mhm.
In other words, the extension is generated by an element of the general linear group over
Right.
L.
Yes, so it will be here.
So you need that extra Q if you have a matrix solution? No. Yes, I guess you do.
So I should
So-
either have something for the matrix solution
With
or
Q to the
for the polar vector solution.
Okay.
I mean I should have,
Yeah, but
and this
You
these
have to
two things
add
are
that
equivalent.
to.
No, but you are ignoring the differential structure. In the sense, for example, if you have the matrix, then you not look. You not only look
Matrix.
at the actual
Its derivative is
solution, but
rational
also its
over the
derivatives,
K.
all up to order n minus 1.
No, but I mean each. So if I have a metric solution, each column in it is
Yeah,
a vector solution.
Oh,
Right.
so you,
It's a vector solution,
he
exactly. But you
prefers
don't
to
care
work with
whether,
that.
right now, in this setup, you don't care whether they are related by the derivatives.
Right, but also here, I mean, even here I already forgot about the differential structure. But what I do remember is the algebraic structure.
Right.
Okay,
So even if I look at the matrix solutions,
okay.
they might have some interesting algebraic relations,
Yeah.
and these algebraic relations will live here.
Will be
because,
there.
Because I'm also taking Cartesian products
Okay,
of any number of factors of Q and C.
okay.
Wait, but you're taking it with the full induced structure, so if there was differential structure on the solutions, like one was the derivative of the
Right.
other, like cosine and sine,
Yeah, so that's, I guess I should
Yeah.
remember that.
It would keep
I
that.
mean,
Okay,
you would end up keeping that
okay,
Yeah,
as a structure on Q.
Right.
sorry.
okay.
No,
No, but the point is that I mean, I
Q
can
under bar.
eliminate the derivative because, I mean, it's a first order differential equation. So
Okay, but if it so happens
What
that
about
the
algebraic
derivative
relations?
is a function from Q to Q,
In the
Then-
constant mystery structure, then no.
then you have kept that structure, right?
The algebraic,
I have kept it, but I don't have to. I mean, but it turns into an algebraic structure.
Oh, I see.
Because-
Okay.
so you take care also of the algebraic
So,
relations.
so
Polynomial
actually, it's just
relations.
algebraic. I mean, the algebraic
X2 could
relations
be
determine
x1
everything.
squared plus,
Okay, one last quick question.
3x3.
I'm wondering the analog of choosing this tilde is in the linear approach, kind of like the same as looking at the small Sanakin category generated by your one.
Exactly. Exactly.
Okay.
Yeah. So yeah.
Do you need to throw this stuff away so that the variety is actually finite dimensional or something?
Yeah, no,
Okay.
the stuff that I throw away just
Neat.
doesn't appear in that
is the
category.
same
but,
for
yeah.
Picard-Vessiot
So this is yeah exactly. But this is exactly analogous to
What's the
to the rings
structure, geometric structure of
tensor
the set?
subcategory that is generated by the equation. And yeah, actually, I can show. I mean, throughout this whole thing, I can show the analogy with what the link does. But notice that okay, but we have a theory in which we already forgot some of the field structure.
Okay, so where the structures inherited.
Yeah. So another way of doing it would be, instead of having just Q, I could have many sorts corresponding to various tensor operations of Q, and then it would mean that instead of having restrictions of polynomial equations, I would just need to consider linear maps between these various things, which is exactly the second category.
So that's
So now a little lemma, which is basically what I already said, is that if we have any differential field extending K, we can have a structure for this. Okay, so if we have some R containing K, we can produce, which is a differential field, we can produce Q of R and C of R. Okay, and this is an equivalence. Between, well, let me say it. So I can do that with any R like that, but in particular I can do it with Picard-Vessiot extensions. So this is an equivalence from Picard-Vessiot extensions over C of R to structures or T-tilde with the C part equal to C of R. Okay? With C part equal to, and Q part of dimension so this is just follows from the fact that R is generated by solutions. Okay, and so and maybe I should. Okay, maybe I shouldn't. Maybe I will not discuss the extra theory. So there is this extra theory that we're interested in, which is this S0, the theory of fields.
Yeah.
And we're interested in knowing what's happening with that. But maybe I'll skip that. But I'll just say that there is an analogous statement. Okay, maybe I'll say it later. Anyway, now I want to say that just by analogy, just because of this, I want to say that a Picard-Vessiot structure, a Picard-Vessiot T-tilde structure, is a T-tilde structure QC with dimension of Q over C equal to just full solution. And see, this is already good news because this lemma means that we're not we're no longer interested in Picard-Vessiot extensions at all. Instead, we can be interested in Picard-Vessiot structures for TTL. Okay? So this is what we're looking for.
I'm a little confused here.
Mm-hmm.
In your T-tutor, isn't T-tutor depending on QC? Or not?
It depends on
QC.
the equation Q.
Yeah, Q and C.
C underbar.
Well, C is
I mean, Q bar under C bar.
so this is.
So, I mean, the notation should be T-tutor sub QC, isn't it?
Well, C bar is
Sub Q.
just
C is always the same.
C
the
is always the
constant.
same.
C is the constant. But yeah, it depends on Q. But since I'm fixing Q, I just don't want to put
No,
notation.
but then when you write something like this here, I'm
Different
not
C.
sure what your T-tutor and the QC, how is the relation between
Oh
the
no,
the
here
original.
I just meant- so what is a T-tilde structure? A T-tilde structure is some set, some two sets. One that interprets Q and another that interprets C. So this is what they call the Q part and the C part.
Is that the same as that Q and
I
that C?
mean, the thing is, which one comes first? Does T-tutor comes first or QC comes first? Or what?
So T-tilde comes first. What is T-tilde? T-tilde is a theory
Right.
in some language that has two disjoint sets
Okay.
and some axioms.
Disjoint.
So what does it mean to give a T-tilde structure? I need to give you a set which I think of as sitting in C, and a set that I think of as sitting in Q, which and some structure that sits here, which satisfy the axioms, or which satisfy the universal axioms. Okay, if it's just a structure. So right. So usually, I mean, in other theories, we're used to have just one sort. So for example, what is a theory of DCF? What is a model of DCF? It's a set together with operations that satisfies some axioms, which are the axioms of DCF.
Yeah.
And so I need to give you just one set and some operations on it. Here I need to give you two sets. This is analogous, but I need to give you two sets instead of one, and I need to give you a bunch of relations on them. And that's what the structure for T-tilde is. Okay? So if I gave you some structure like that, it has a C part, what I think of as C, and it has a Q part. Okay? And so one way to give a structure is to give a differential field. And then if I give you a differential field, you look at the set of constants, this will be the C part, and you look at the set of solutions, and this will be the Q part. But now I'm saying that in fact, I don't need to give you a whole differential field. I could just give you a field, a vector space, which is of dimension at most n, and some relations. Okay?
And what does equivalence here mean?
Equivalence of categories. So this is the
categories.
this is the equivalence of categories.
The R star differential overfields, okay.
So on the left side, I have Picard-Vessiot extensions in the sense that I defined before, and here I just have structures for the
And R is R a differential K algebra or a differential field?
is it
R.
the differential field? It's a Picard-Vessiot. It's a Picard-Vessiot extension.
Over C of R.
Okay.
So I think I'm confused about all the different C's. There's
Okay.
a Q bar, a C
So-
bar, a Q of R, a C of R, and a Q and a C.
Those are
Right.
rational, rational point. They're just rational points.
Yeah, exactly.
No, I'm sorry, I didn't hear
So-
your answer.
What?
Okay.
So
C.
yeah. So Q. I guess I should also put under.
It's
So
Q bar.
Q and C are differential equations. Q is the differential equation we start with, and C is the differential equation x prime is equal to 0
With coefficients in.
in K. I mean, this one is with coefficients in K. This one is in coefficients in Z. But
And C of R and Q.
so Q of R is the set of solutions of Q in R. And C of R is the set of solutions of C in R, which is known as the field of constants.
Ah,
C sub
okay.
R.
So it's the induced substructure.
Yeah, so I take a differential field R, and I just take the solutions of Q in it, take the solutions of C in it.
Right,
So that gives me two sets.
right.
I have plenty of relations. They're coming just from the relations in the field, and these relations correspond to relations here, and that's how I
Right.
interpret the relations.
So C bar of R is contained in C bar?
So it's
No,
two different
no.
things. C bar is an equation, is a syntactic thing. It's a
C
formula.
bar of R.
C bar of R is the set of solutions of that equation.
C bar of R? Huh?
So this is what you
This is C
usually
sub R.
call CR.
These are the definable sets.
Those are C.
It's
Yeah.
it's a set of all solutions of the equation x prime equal to 0 in R. So this
Okay.
is
And what
so
about
for any definable set?
Q and C? Q and C.
They're just
Which you see?
formulas. They're just
Those are-
equations,
Yeah.
not solution sets of those
No,
equations, but
and
just
then-
those equations.
Yeah, but then I could have an abstract detailed structure that a priori doesn't come like that. So
Yeah.
what is a two-tailed structure? It's some set Q and another set C, and C happens to have a field structure, and Q happens to have a vector space structure over C of dimension at most n, and then there's a bunch of relations, of other relations that you have on it. So this is a QC, this is a T-tailed structure, and I'm just saying that one of the interesting part of this statement is that this structure is actually the set of solutions of these equations in some
In some.
differential fish,
Right.
which is a Picard-Vessiot.
And QC?
At the bottom, yeah.
So QC is this structure. So is a PVT structure is a T-tailed structure. M. So what is a T-tailed structure? It has two parts, the C part and the Q part. The C part I denote by C of n. So I have C of m and Q of m. So Q of m is the Q part of m. So I already know that it's a vector space of dimension at most n, and I want it to be of dimension n
Right.
over C of n.
Yeah.
So this is a definition now.
This is a definition. But it's not, it's not an important definition because if I had time, I would generalize it to a more general case. But maybe, I don't know, I say I have minus 2 minutes or 2. Maybe I'll just very briefly say what is the structure now.
Do you want to stop?
2 minutes.
2 minutes. That seemed to be the consensus at this
Give
table.
them till noon.
Yeah. What about till noon?
What?
Till noon?
It's too
No,
long.
no, so they have to leave.
Oh,
they
the
have
lunch
to
gets
come.
crowded.
We want them to hear it.
Let me, in 2 sentences, just say what's going on next. So now we have these two theories. We have T-field, and we have T, which I didn't mention here, which is just ACF CK. Okay, algebraically closed fields with constant symbols for CK, and I have a part. So T has 2 parts, Q and A and C, and this C part is a model of that. Okay, the C part is a model of that, so it's an algebraically closed field, and the Q part is not a model of that, but it's not very far from being a model of that. Namely, if I add a basis, then I can already somehow identify between them.
Yeah.
Okay, and so
So he doesn't need a
this thing is an example
Yeah.
of what we call an internal cover. Which I don't want to define now, but it's a completely abstract definition in model theory. So it's just some relation between two theories. Okay. And the definition of an internal cover is such that you can define the analog of a Picard-Vessiot structure, like I did here, but in general for an internal cover. And so then you can make another step and identify. So this is what I call Picard-Vessiot structures. In general, so Picard-Vessiot structure is something that is defined in general for an internal cover. So now that's it. We reached the satisfying situation that we have no more fields. And this is completely abstract now.
I'd call that unsatisfactory.
And from now on, everything just works in general. So you have the analog of a Picard-Vessiot structure. And then you can make another step and talk about a particular set of interpretations of T tilde in T, whatever it means. So this again corresponds to Picard-Vessiot structures. And then the point is that these are classified. So Picard-Vessiot structures are classified by a definable groupoid in T. Okay? So there is a definable groupoid in T whose objects correspond essentially. What I'm saying is not completely true, but essentially its objects are Picard-Vessiot structures. But its objects, so it's a definable groupoid, so you can ask what are the points of this groupoid in some T structure L, and the answer is it's going to correspond to Picard-Vessiot structures over L, so whose T part is L. And now again. What do you want? You want to find the Picard-Vessiot structure over 0, so with no parameters. So which means that you want to find the point of the set of objects of that groupoid, the definable set of objects there, which is over 0 or over whatever parameters you started with. But now, what you know that the parameters you started with, it's existentially closed in K. So if you find a Picard-Vessiot extension over K, means you found a K point of this groupoid, then the existential closure automatically provides a C point, which is what you're looking for. So this is a bit vague, but this is the strategy, and this is if you know the Lin's argument, you see that it's exactly analogous, but here it works in a very general context.
So there's no Tanakan theory that you get a groupoid from. It's just more general thing.
So this theory of internal covers is an analog of a Tanakan theory, but it applies in a much wider context.
Yeah.
Even in the context of differential equations, there are, for example, these strongly normal differential equations. So there, again, I didn't check, but I'm sure you can get very similar results because it's again just a different internal cover. But on the other hand, there's no Tanakan formalism there because it's non-linear groups. So just also. Any questions?
Well, we can save them for the afternoon.
For the afternoon.
You're gonna meet in the afternoon?
Yeah,
No, I can't.
Yes.